Welcome everyone. Today for the fractional calculus seminar series, today we have Professor Yuri.Luchko, who is a full professor at the Faculty of Mathematics, Physics, Chemistry of the Berlin University of Applied Sciences and Technology in Germany. He studied mathematics at Belarusian State University in Minsk and received his PhD from the same university in 1993. In 1994, Professor Yuri.Luchko got a postdoc position at the Free University of Berlin, Germany, under the supervision of Professor Rudolf Gorenfellow, and stayed there for 6 years. From 2000 to 2006, he was a scientific researcher at the University in Frankfurt Oder, Germany. In 2006, Professor Yuri.Luchko got a professorship at the Technical University of Applied Sciences, Berlin, Germany. The main research field is applied mathematics with special focus on fractional calculus and its applications. Professor Luchko has published about 200 papers in international peer-reviewed scientific journals and about 20 books and book chapters as an author or editor. He is also an associate editor of the International Journal of Fractional Calculus and Applied Analysis and the editor of several other reputable mathematical journals, including ZAA. We are very happy to have you here, Professor Luchko. You may please begin the talk.
Thank you very much, Pavan, for a nice introduction. And first of all, let me thank the organizers of the seminar, Arran and Pavan, for their work and for inviting me to present my recent results also this year. The title of my today's talk is Fractional PDEs involving general fractional derivatives with Sonin kernels as anomalous diffusion models. I'll start with a short introduction and motivation for this work. Then I remind you on the general fractional integrals and derivatives with Sonin kernels, and then introduce the fractional evolution equation with the general fractional derivatives with Sonin kernels, and discuss its relationship to the continuous time random walk model. Starting from the continuous random walk model under some assumptions on the asymptotics of the corresponding probability density functions, we then derive a fractional diffusion equation with the general fractional derivatives and consider its properties and some examples. This is our plan. And first of all, let me start with some short motivation for this research. If we consider the so-called complex systems that are characterized by a large diversity of different components and strong interaction between these components, and this leads to anomalous evolution of the systems in time. In particular, usually the standard conventional laws like Fick law, Gaussian statistic, and so on, they are not valid for transport or diffusion processes in complex systems. And this leads to a deviation from the linear time dependence of the mean square displacements of the diffusing particles. So this classical formula, the last one on the slide, is not valid. Instead, the mean square displacement of the diffusing particles can be described by nonlinear functions, and the most investigated and probably most important and famous case of models for anomalous diffusion deal with the case of the mean square displacement in form of a power law function, t to the power alpha. In the case alpha is equal 0 and 1, we have the so-called subdiffusion or low diffusion. In the case alpha is between 1 and 2, fast diffusion or super diffusion, and the case alpha is equal to 2 corresponds to the so-called ballistic diffusion. This behavior of the mean square displacement can be described or imitated by models in form of fractional PDEs with different kinds of the fractional derivatives. Currently, we have a huge amount of publications devoted to this case. Elaborated mathematical theory is available, and there are several applications case study available. However, in some applications, the mean square displacement deviates also from the power law with a fixed exponent, and thus in this case one needs some more general models, anomalous diffusion models. Until now, several models of this kind were already suggested, like models in form of fractional PDEs with the multi-term fractional derivatives, with the distributed order fractional derivatives, and with the variable order fractional derivatives, as well as fractional PDEs with the general fractional derivatives with Sonin kernels. And our focus today will be on this class of models of anomalous diffusion in form of fractional PDEs with the general fractional derivatives with Sonin kernels. Then let me start with short introduction to the general fractional integrals and derivatives. And the story began with a publication of Sonin 1884. And in this famous work, Sonin introduced the so-called Sonin kernels. These are two functions, kappa and k, that satisfy a very simple so-called Sonin condition, namely that their convolution, Laplace convolution, standard Laplace convolution, is equal to 1, identically equal to 1 for all t greater than 0. Some examples of the Sonin kernels are on this slide, and the most known and probably most important example of the Sonin kernels are kernels in form of power law functions, h alpha and h1 minus alpha, where the denotation h alpha is equal to t to the power alpha minus 1 divided by the gamma function of alpha is used. We will use this denotation later on. In the paper by Sonin, he derived another pair of kernels in terms of the Bessel function and the modified Bessel function. Also very famous case of Sonin kernels. However, today, as a special example, we will use another pair of the Sonin kernels. The first one, the kernel kappa, is in terms of the two parameters Mehta-Cliffler function with a power law factor, t to the power alpha minus 1. And the second function, k, is a sum of two power law functions. To the best of my knowledge, this pair of Sonin kernels were first mentioned by Andrzej Haniga in one of his publications. However, there exist many other Sonin kernels in terms of elementary and special functions. See, for example, this paper by Samko and Cardoza, published in 2003, where a lot of particular Sonin kernels are mentioned. Well, nowadays, in the theory of the general fractional integrals and derivatives, one works normally not with particular Sonin kernels, but with some classes of the Sonin kernels. And the first and probably also most important class of the Sonin kernels was introduced by Kochubey in his famous paper published in 2011, where he introduced the class K of Sonin kernels that satisfy certain conditions in terms of the Laplace transform of one of this kernel. So you see here three conditions, K1, K2, K3, and K4. And in particular, in our derivations, we will use the conditions K3 and K4, but not, for example, the condition K2. That is a very strong condition that the Laplace transform of the function K is the Stieltjes function. Well, recently another more general and larger class of Sonin kernels, the class L-1, was introduced, and this class consists of Sonin kernels that belong to the space of functions C-1. And the space of functions C-1 consists of all functions in the form power law function with the exponent p greater than -1 multiplied with a continuous function f1. These kernels possess integral singularities of the power law type as the origin, and many results regarding the general fractional derivatives and integrals with these kernels can be derived for the Sonin kernels from this class. Of course, there exist Sonin kernels with other types of singularities, but these are already very specific Sonin kernels, and in the class L-1, in fact, a very big set of Sonin kernels is already included. For the theory of this of the operators with these kernels, I refer to these recent papers. Well, now we introduce the general fractional integrals and derivatives with the Sonin kernels, and we suppose that kappa and k are Sonin kernels. Then the general fractional integral with the kernel kappa is defined just as a convolution of the kernel kappa with the function f, Laplace convolution. So the general fractional integral is just a Laplace convolution type integral. The general fractional derivative with the kernel k and the regularized general fractional derivative with the kernel k, respectively, are defined as in form of the composition of the first order derivative and the Laplace convolution of the kernel k with the function f. Or in other words, it's nothing, the general fractional derivative is the first order derivative applied to the general fractional integral with the kernel k. Then in the paper by Kochubey that I already mentioned, the so-called Caputo type general fractional derivative or regularized general fractional derivative was introduced in this form. And this definition, we will see later that this second definition is more convenient for, especially for applications, because in the differential equations with this regular general fractional derivatives, initial conditions in standard form, in local form, can be included. Well, the term regular general fractional derivative can be explained by this last representation, the last formula. You see here that the regular general fractional derivative is a general fractional derivative applied to a regularization of the function f at the point 0. And of course, this second form, this last form of the regularized general fractional derivative is also valid under on some appropriate spaces of functions. Well, the famous and important particular cases of the general fractional integrals and derivatives are the Riemann-Liouville and Caputo fractional derivatives with the kernels, with the power law kernels H alpha and H1 minus alpha, Also multi-term fractional derivatives with the kernel k in form of a finite sum of the power law kernels, the so-called fractional derivatives of distributed order, where the kernel k is in form of a integral of a power law function with respect to the parameter alpha, where rho is a Borel measure defined on the interval from 0 to 1, and also many other new and known fractional derivatives are particular cases of the general fractional derivatives. Well, let's shortly mention some basic properties of the general fractional integrals and derivatives. For the general fractional integrals, the index law in this form is valid. You see that the composition of two general fractional integrals with the kernels kappa 1 and kappa 2 is nothing else than the general fractional derivative with the kernel kappa 1 Laplace convolution with kappa 2. On appropriate spaces of functions, the general fractional derivative with the kernel k and the regularized general fractional derivative with the kernel k are left inverse operators to the general fractional integral with the kernel kappa. And also the so-called second fundamental theorem of fractional calculus is valid if you consider the compositions of general fractional integrals and derivatives. Then we get the function f and an additional term. And this additional term, in both cases, determines a natural initial condition, a natural form of the initial condition while dealing with the fractional differential equations with these derivatives. As you see, in the case of the general fractional derivatives, the initial condition is expressed in this unusual form in terms of the general fractional integral with the kernel k, while in the case of the regularized general fractional derivative with the kernel k, the initial condition is given in its usual form. For more details, please see this paper where you find more information and also applications. Well, now let's shortly mention some ideas behind the continuous time random walk models that will be also one of the main players in our today's presentation. Of course, all of you are aware of these ideas. And this model is based on interpretation of a diffusion process on the micro level as a stochastic process. Thus, behavior of the diffusing particles can be described in terms of the probability U of an individual particle to be located at the point x at time t. And this function U satisfies the so-called master equation and is connected with the so-called displacement or jump PDE, lambda, and the waiting time PDF psi that characterize the diffusion process. These functions are supposed to be known, and in the framework of this continuous time random walk model, one looks for determination of the function U. Here on this diagram, we have a typical behavior of a particle under one-dimensional continuous time random walk process. As you see, this particle can stay at some points for different times, and then this particle jumps suddenly to other locations, and both the waiting times and the distribution of jump lengths are characterized by corresponding probability density functions. Well, under assumptions that there is no correlation between displacements and waiting times, and that at the time t is equal to 0, the random walker is located at position x is equal to 0. One can write down the so-called master equation for the continuous time random walk model. This equation, integral equation, is nothing else as an expression for the total probability, law of the total probability applied to the probability u to find the random walker at the location x at time t. And in this equation, in fact, standard equation, known to everybody involved in this topic, and the function psi capital is the so-called survival probability that is connected with the waiting time probability function psi by using this formula. Well, if we apply the Fourier and Laplace transform to this formula, to this master equation that is expressed in terms of the convolution, Laplace convolution and Fourier convolution, then we easily get this formula. And from this formula, we can determine the Fourier Laplace transform of the function u in this form. And the Laplace transform of the survival probability is connected with the Laplace transform of the waiting time probability density function psi by this formula. So substituting the second formula in the first formula, we finally arrive at this very well-known formula for the Laplace, for the Fourier Laplace transform of the function u. This is very known formula, nothing new. So another component of this series that I would like to present you today is the so-called general fractional evolution equation involving the regularized general fractional derivative with the Sonin kernel K. This equation is given in this form. You see here at the left-hand side the regularized general fractional derivative with the kernel K. This is a time fractional derivative. At the right-hand side, we have a certain spatial pseudo-differential operator with this symbol A of zeta. That means that the Fourier transform of the operator at the right-hand side can be expressed in this form. Some example of the operator Lx are, for example, the Laplace operator with the symbol minus zeta squared, or operators in the form of the continuous and discrete Fourier convolution with the symbols equal to Fourier transform of the transition function omega. All this and other operators are included here in this general fractional evolution equation. And now we can transform this evolution equation from the differential into integral form. So if we take the standard initial condition at the point t is equal to 1 in form of the Dirac delta function, then the first fundamental theorem, the second fundamental theorem for the regularized general fractional derivative leads to the following integral equation. In other words, we just apply the general fractional integral with the kernel kappa to the first equation and use the initial condition, and then we get this integral form of the general evolution equation. Well, this equation is also in form of Laplace convolution, and the Fourier transform of the operator L x is also known in terms of its symbol. Thus, we can now apply the Fourier and Laplace transforms to this equation. It's also not difficult to see that we get this formula that can be solved regarding the Fourier Laplace transform of the function u. And we get this formula, this final formula. Well, now let's consider interrelation between the fractional evolution equation that we introduced some minutes ago and the continuous time random walk model. As we already mentioned, the continuous time random walk model is described by two degrees of freedom, namely by the waiting time PDF psi and the displacement PDF lambda. The fractional evolution equation involves also two degrees of freedom, the Sonin kernel kappa in the integral form, and the symbol A of the pseudo-differential operator. If we discuss the question about the interrelation of these both objects, then in fact, from the mathematical point of view, this question is reduced to the question if the functions psi and lambda and the function kappa and A are interrelated, and what is the relation between them. So to clarify this question, we suppose that the general fractional evolution equation and the continuous time random walk model describe the same diffusion process. This means that their solutions are identically equal, and correspondingly, the Laplace Fourier transforms of the solutions are also identically equal. Here, in the last formula, we see both Fourier Laplace transform of the solution to the continuous time random walk integral equation and to the solution to the general evolution equation. So in this equation, if we write down this equation, then it turns out that the variables, both independent variables zeta and s, by just elementary transformations, can be separated. So this first equation is equivalent to the second equation, and because the variables, the Fourier variables theta and Laplace variable s are independent from each other, the only possibility for validity of this equation is that both sides are equal to the same constant. So from this equation, we get two important relations. So the first formula connects the Fourier transform of the displacement PDF lambda of the continuous time random walk and the symbol A of the general evolution equation. And in the second formula, we have a connection between the Laplace transform of the Sonin kernel kappa and the Laplace transform of the waiting time probability density function psi. Thus, as already said, both models, continuous time random walk model that is determined by the probability density functions psi and lambda, and the fractional evolution equation that is determined by the kernel kappa and the symbol A of the pseudo-differential operator. They describe the same diffusion process only when the following two relations are valid. Yeah? So in a certain sense, these models are related. I would not say they are equivalent. There are some nuances here, but they are interrelated, and their relation is given by these two formula. In what follows, let's consider, without loss of generality, the case C is equal to 1. And we focus on the second formula first. This second formula can be solved with respect to the Laplace transform of the function psi. And if we do this, then we get this connection. And now we assume that the Laplace transform of the function of the Sonin kernel kappa tends to 0 as S tends to plus infinity. And this is exactly the condition K3 for the Sonin kernels from the Kochubey class K. So it's a very natural condition. In this case, we can use the power law expansion of this function. And finally represent the Laplace transform of the function psi in form of this series. Yeah? This series contains power functions of the function of the Laplace transform of the function kappa, and thus we can return to the time domain by applying the inverse Laplace transform to this last formula, so that the waiting time PDF psi can be represented in this form of the so-called convolution series. Yeah? What we have here are convolution powers, so-called convolution powers that are defined by this relation. The convolution power n of the function f is nothing else than the n-fold convolution of the function f with itself. The series of this form with convolution powers are called in the fractional calculus literature as convolutional series, and especially the case of the special coefficients an that are in form of a power laws, mu to the power n is very important. This function that is denoted here by L kappa mu plays in the fractional calculus, generalized fractional calculus, in fact, the same role as the exponential function plays in the conventional calculus. Using this denotation, we can represent the waiting time probability function psi in form of L kappa minus 1, in form of this convolution series. Well, this representation has some very useful and, in my opinion, important consequences. Namely, in the theory of fractional differential equations with the general fractional derivatives, solutions to some equations were represented in terms of the convolution series L kappa mu. And it was, in particular, it was shown that L kappa mu is a solution to this fractional relaxation equation with the general fractional derivative with the kernel K. Please Please take a note that we have here not the regularized general fractional derivative of Caputo type, but the general fractional derivative of the Riemann-Liouville type, and thus the initial condition is given in terms of the general fractional integral. Because the waiting time probability function psi can be represented in terms of this convolution series L kappa minus 1, we immediately get the result that the function psi is nothing else than the solution to the fractional relaxation equation with the general fractional derivative with the kernel k. This last formula provides a bridge between the continuous time random walk model and the fractional relaxation equation. To the best of my knowledge, this connection was not mentioned yet in the literature. For more results regarding the fractional differential equations with the general fractional derivatives, I refer the readers or you to this recent paper. Now let's consider an example, very important example. If we take the kernel kappa equal to H alpha, this is exactly the kernel of the Riemann-Liouville fractional integral, then we can calculate the convolution powers in explicit form. Convolution powers are again just power law functions. And then we write down the representation of the function psi in terms of the convolution series. Insert the definition of the function h, and finally we arrive at the expression in terms of the Mehta-Cliffler function of the two parameters Mehta-Cliffler function. And thus we arrive at the result that was derived first in the paper by Hilfer and Anton, published in 1995, namely in the case of the fractional evolution equation with the Riemann-Liouville fractional integral or Caputo fractional derivative in differential form. This equation can be embedded into the framework of the continuous time random walk with the waiting time probability function psi in form of the two parameters Mehta-Cliffler function. The main point here is that this embedding is a real embedding, not in the asymptotical sense. Now let's proceed with derivation of the so-called general fractional diffusion equation involving the regularized general fractional derivative from the continuous time random walk model. And this time, this derivation will be in the asymptotical sense. Thus, the idea behind this derivation is that we first derive some suitable asymptotics of the displacement PDF lambda and the weighted type PDF psi, and then use this asymptotic to derive in general fractional diffusion equation. The first assumption is that the displacement PDF lambda possesses a finite variance, and without loss of generality, we set this variance to be 2, and then we get the known asymptotical formula, the Fourier transform of the function lambda behaves like 1 minus zeta square in the case zeta tends to 0. As to the waiting time probability density function, we already derived this formula, this connection with the function, with the Laplace transform of the function kappa. And the Sonin condition in the Laplace domain looks like this. You remember that in the time domain, the Laplace transform of kappa and k is identically equal to 1. And if we apply the Laplace transform to the Sonin condition, then we get this formula. And this second formula allows us to get a connection between the Laplace transform of psi and Laplace transform of the function k. So if we express Laplace transform of the function k through the Laplace transform of the function kappa from this second formula and insert it into the first formula, then we easily get this third formula. And now we use the condition K4, K4 for the Kochubey, for the kernels from the Kochubey class K. And this condition says that S multiplied with the Laplace transform of the function K tends to 0 as S tends to 0. Thus, we can easily derive asymptotics of this of the right-hand side of this expression in the form Laplace transform of the function psi behaves like 1 minus S multiplied with the Laplace transform of the function k as S tends to 0. Then we have two asymptotical formula. The first one for the Fourier transform of the function lambda. The second one for the Laplace transform of the function psi. And then we substitute these formulas into the Fourier Laplace transform of the solution to the continuous time random walk integral equation and get this asymptotical relation. First, that can be easily reduced to this one. Yeah. So in the case lambda and psi satisfy the asymptotical formulas above, these two asymptotical formulas, the solution U of the continuous time random walk integral equation satisfies these asymptotics for small s and zeta. Well, now let's take a closer look at the last expression, and it's easy to show that the fundamental solution of this fractional diffusion equation in the form regularized general fractional derivative with the kernel k with respect to time is equal to the Laplace operator equipped with the initial condition in form of the delta function. So it's so-called fundamental solution has exactly this form that we have that we had on the previous slide. Yeah. And of course, this form is very easy to get by using the Laplace transform formula that is valid for the regularized general fractional derivative with the kernel k. Thus, we arrive at the following result, that the fractional diffusion equation, this general equation with the regularized general fractional derivative with the kernel k, can be deduced from the continuous time random walk model with the waiting time PDF satisfying this asymptotical behavior and the displacement PDF lambda satisfying this behavior. And thus, this general fractional diffusion equation can be considered or treated as a mathematical model of the anomalous diffusion processes. In what follows, we discuss some relevant physical and mathematical properties of its solutions. First, following remark, this general fractional diffusion equation that we derived from the continuous random time work model in asymptotical sense is evidently a particular case of the general fractional evolution equation that we had before with the pseudo-differential operator Lx with the symbol minus zeta squared. Well, one of the main characteristics of the continuous time of the models for anomalous diffusion is the mean square displacement of a random worker governed by the corresponding equation. And let's determine the mean square displacement of a random worker governed by the general fractional diffusion equation that we derived on the previous slide. To do this, we use this known formula in terms of the nabla squared with respect to the psi variable applied to the Laplace Fourier transform of the solution U evaluated at the point zeta is equal to 0. In our case, the fundamental solution, the solution we have to examine looks like this. With some routine calculations, we can derive explicit formula for nabla squared of this expression. This formula looks like this. And now we have to substitute zeta is equal to 0 into this formula, and of course change the sign. And the result is very, very simple. In the result, we get a very simple expression of the mean Laplace transform of the mean square displacement of the random worker governed by the general fractional diffusion equation in terms of the Sonin Laplace transform of the Sonin kernel kappa. Of course, this formula can be translated back to the time domain. If we apply the inverse Laplace transform to this formula, then the mean square displacement can be expressed in form of 2 multiplied with a definite integral of the kernel kappa, or in terms of the convolution of 1 with kappa, and 1 can be represented in terms of this function h. 1 is nothing else than h1. So we derived this very simple and elegant formula for the mean square displacement. And now let's consider some examples. Let's start with the well-known case of the power law Sonin kernels. The kernel kappa is equal to h alpha, and the kernel k is equal to h1 minus alpha. The general fractional diffusion equation takes this form that was already investigated from the mathematical point of view and also in applications. So at the left-hand side, we have just the Caputo fractional derivative of the order alpha. And then here at the right-hand side, we have the Laplace operator. And if we apply our machinery now, then we can derive the mean square displacement of a random worker governed by this fractional diffusion equation by using the formula we derived, namely 2 by convolution of h1 and h alpha, that is h1 plus alpha. And finally, we immediately derive this very well-known formula in form of a power law function valid for the mean square displacement of this equation. This formula is not new, of course. This was derived by Schneider and Wyss in their paper published in 1989, and then by Hilfer and Anton in the paper published 1995. So this is a very well known result. However, this result was derived, of course, by just using the technique of integral transforms, Fourier and Laplace integral transforms, and without any convolution series. Our approach allows us to consider more complicated cases, more complicated equations. And if we take the kernels, if we take the kernel K in form of these two power law functions, and the corresponding kernel kappa is expressed in terms of the Mehta-Leffler function with two parameters, then the general fractional diffusion equation is nothing else as this multi-term fractional differential equation. So at the left-hand side, we have a sum of two Caputo fractional derivatives. At the right-hand side, we have the Laplace operator. And then we can apply our formula and explicitly calculate the mean square displacement of the random walker governed by this equation. And here we have to calculate convolution of H1 with this Mehta-Leffler function with two variables, and then we get another Mehta-Leffler function also with two variables. In particular, we can use the known asymptotical behavior of the two parameters Mehta-Leffler function to derive asymptotics of the mean square displacement at the point 0 for small times and at infinity for big times. And you see here that the mean square displacement has a crossover behavior from small times to large times and with different exponents. Yeah, and as also already mentioned, in some applications, behavior like this, behavior of the mean square displacement of this kind was established experimentally. So maybe one can try to employ models of this kind. Well, another example is that we take, in fact, the same Sonin kernels, sum of two power law functions and Mehta-Leffler function with two parameters, but in different sequence. So now the first Sonin kernel K is expressed in terms of the Mehta-Leffler function, and the second kernel kappa is taken in terms as a sum of two power law functions. The general diffusion equation with the kernel K takes then this form with the so-called this is a special fractional derivative that was already considered in the literature. There were several publications devoted to this case. This is a general fractional derivative that look like this. Yeah, this is just a Laplace convolution of this Mehta-Leffler function with the derivative of the function f. This is the form of the regularized general fractional derivative with the kernel K in this form. Yeah. So the fractional derivative, time fractional derivative, is given by this formula. And at the right-hand side, we have the Laplace operator. Then we can employ our machinery and calculate in explicit form the mean square displacement of the random walker governed by this fractional diffusion equation. And the end formula is the sum of two power law functions. Again, we can calculate this time very easily asymptotical behavior of the mean square displacement. And again, we have crossover behavior between small times and large times. Well, now let's consider some important mathematical properties very shortly. These are known results, but I just wanted to mention them that are already were already derived for the general fractional derivative with the regularized general fractional derivative with the kernel K. In the paper that I already mentioned, in the paper by Kochubey, published in 2011, he showed that the solution to the Cauchy problem on the whole domain Rn, in the case the initial condition U0 is a bounded globally held continuous function, the solution to this problem is locally integrable, infinitely differentiable, and can be interpreted as spatial probability density function involving in time. So it's a very important mathematical property that also speaks for possibility of employing models of this kind as anomalous diffusion models. And another mathematical property, also very characteristic for diffusion type processes, is the so-called maximum principle for solution. And this question was considered in this paper published in 2016, where the initial value problems for the general fractional diffusion equation in the same form, but on bounded domain, bounded spatial domain, was investigated with initial condition and with boundary condition on the boundary of the domain omega, that is a bounded domain in Rn. And under some conditions for the Sonin kernels that are slightly different from the conditions posed by Kochubey in his theory, these conditions are weaker than the conditions posed by Kochubey. It was shown that the solution to the initial boundary value problem that we have here on this slide with the initial and boundary conditions, that the solution satisfies the maximum principle. That means that if the inequality, this inequality is valid, then the solution U of this inequality takes its maximum either at the initial time t is equal to 0 or on the boundary of the domain omega. Once again, of course, this is a mathematical result, but very important for applications because by any anomalous, by any diffusion process, normal or anomalous diffusion process, of course, fulfillment of maximum principle is expected from the physical point of view. Well, I have just 1 minute, and I hope to complete my talk in 2 minutes. Sorry. As to the references, I already mentioned some of these papers, the paper by Kochubey, Hilfer and Anton, and so on. These papers, these publications concern the theory that was presented here, but it's also important to mention some papers that are devoted to applications of the general fractional equations with the general fractional derivatives. In these papers by Atanaskovich and his co-authors, Bashlyakova, Tarasov, and so on. They employed this general fractional calculus, the general fractional derivatives with the general fractional derivatives with the Sonin kernels for modeling of different physical phenomena. And last but not least, let me mention that this talk is mainly based on the recent paper written jointly with Mariam Al-Kandari from the Department of Mathematics, Kuwait University, and Dmitry Luchko from the Institute of Industrial Studies, Tokyo University. And this paper was published in the framework of a project funded by the Kuwait Foundation for the Advancement of Sciences. So thank you very much for your attention. Questions and comments are welcome.
Thank you very much, Professor Luchko, for the very nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen. I'm not able to see any raised hands, but if you have a question, you can unmute your mic and go ahead.
Oh, maybe I can ask a question. For example, both Andrzej and Katarzyna and Francesco are very good experts in the anomalous diffusion processes and models and continuous time random walk models. What is your opinion? Would this general model of anomalous diffusion processes in terms of the fractional differential equations with the Sonin kernels make sense for applications? Would it be useful potentially for applications?
Okay, so during my talk at the end of August, I've wanted to try to convince you that yes, it is really very helpful using the Sonin kernel. Yuri made it in the more easy way as but yes, we can apply it and we apply it very often of it. So it is very close connection with the physics, with diffusion, and also with relaxation processes.
Yeah. Look, and I think that especially this non-standard asymptotical behavior of the mean square displacement would be potentially very useful. I read some papers from applications that describe processes or measurement data with the mean square displacement of this kind. So as far as I understood, it's I mean I'm not statistical. I'm not expert in stochastical processes, but in these papers, the authors said, well, we are not happy with the power law asymptotics of the mean square displacement of models of this kind. We need asymptotical behavior that possesses a kind of crossover between different kinds of asymptotics for small times and larger times, for example.
Okay. If I can say something, this Sonin kernel, which is written in this slide 38, was used by the Stanislavski and Veron. Because here we are talking about the Sonin pair. And as you know, it's related with the completely Bernstein function. Of course, I'm using the word of Schilling and Vondracek, such notations. And because Anatol Kochubey assumed that they are the Stiltes functions. And when we invert them, it is the completely Bernstein functions, and for completely Bernstein function exists the pair of completely Bernstein function, which gives that their products are equal to ours. So they are using such words, not Siltius functions, but completely Bernstein functions, and they are using such pair. So this I can only say. Okay.
Yeah, very nice. Thank you for your comments, Katarzyna.
No, it was really pleasure to hear you. Okay.
Are there more questions or comments or any final remarks if there are none? I guess no. So this is a very good point to stop this talk, close this talk here. Thank you very much, Professor Luchko, for this for this nice talk. It was very nice having you here today.
Thank you for inviting me.
It was a pleasure for us.
See you
too.
next time.
Yes.
Next